SRF are purposefully engineered manure which can delay the nutrient release in a way that each single application could meet the plant's growth requirement. It is produced by encapsulating urea in hydrophobic material that restricts the dissolution of urea in water, thus preventing economic losses and environmental pollution. A diverse range of materials have already been utilized for SRF, but their non-biodegradability, hydrophilicity, brittleness poses challenges and often require modification, which increases the overall cost. Moreover, the production of SRF involves the usage of harmful solvents and the products are mononutrient.
Now let me explain you how we actually produce this multi-nutrient slow-release fertilizer. We actually invented a methodology which does not involve the usage of any harmful solvent which pollutes the environment. We took 60 ml of glass vial. In that glass vial, we put 4 grams of sulfur and 8 grams of urea and placed that mixture inside the thermoset oil bath preheated at 170 degrees Celsius to melt the sulfur and urea. Why are we melting sulfur? Actually, the melting of the sulfur initiates the ring opening process of the sulfur, which generates the diradical at the end of the sulfur chain. After the melting of sulfur, we pour 4 grams of sulfur inside that mixture and let that mixture to react for 1 hour. Inside this glass vial, this reaction occurs, which involves the ring opening process of the sulfur and then the reaction of the diradicals with the rubber seed oil. Urea neither reacts with this sulfur nor with the rubber seed oil. It only gets embedded inside the structure of the polymer. We already have published one paper on the polymer. As you can see the published paper on your screen.
After producing this multi-nutrient slow-release fertilizer, we did some laboratory testing to prove our hypothesis. Fourier transform infrared spectroscopy was carried out to elucidate the interaction between urea and copolymer. The FTIR spectra shown depicts the spectrum of urea, copolymer and fertilizer. The spectrum of urea shows the peaks for amine stretching at around 3400 and 1590 per centimeter of wave number, along with the stretching peaks for CN and CO. Similar peaks are appearing in the spectrum of the fertilizer without any chemical shift, which confirms that no reaction has occurred between sulfur and urea and also between rubber seed oil and urea. The only reaction has occurred between the sulfur and rubber seed oil, which is evident from the appearing of CH stretching in the spectrum of the fertilizer, which confirms the formation of the fertilizer composite and also the physical interaction of the urea. The SEM micrograph shown revealed the composite morphology of the produced fertilizer. The red circle represents the urea particle embedded within the structure of the polymer. It also confirms the uniform distribution of the urea particle over and within the fertilizer. To test the nitrogen release longevity of our produced fertilizer, we did nitrogen leaching test in distilled water. Firstly, we calculated the total nitrogen content of our produced fertilizer using Kedergel method. After that, we placed 2 grams of our fertilizer in 200 ml of distilled water in aluminum flask placed in incubator shaker at speed of 220 rpm. Similar experiment was repeated for pristine urea as a control experiment. As you can see, the pristine urea releases almost 99.5% of its total nutrient in first 24 hours, whereas our produced fertilizers only releases 12% of its total nutrient in first 24 hours. European standard states that the fertilizer should not release more than 15% of its total nutrient in first 24 hours, which means our fertilizer perfectly follows the European standard. It took almost 35 days to release 75% of its total nutrient for our fertilizer in distilled water.
Containing nitrogen as a nutrient sealed in a polymer coating when applied to soil. The water penetrates the pores of the polymer, generated by dissolution of surface nutrients, dissolve the nutrient and release to the plant. It delays the nutrient release to such point that its single application is enough for whole growth process of the plant.
The best thing is our produced fertilizer not only delay the release of nitrogen in accordance with the plant nutrient requirement, it also releases sulfate as a secondary nutrient which is required by plant for their growth. This fertilizer is designed in such a way that it contains sulfur chain in its backbone which get oxidized to sulfate in presence of Aspergillus niger bacteria which is present in soil. To test the sulfate release from our fertilizer, we adopt submerged cultivation methodology which uses the barium sulfate precipitation to calculate or to estimate the amount of sulfate released from the fertilizer. Sulfate release test of the produced fertilizer revealed the 50% superior sulfur oxidation compared to elemental sulfur, which is due to the presence of carbon chain in the structure of the polymer which supports the bioprocess of the sulfur oxidation to sulfate. In conclusion, FTIR revealed the physical interaction between urea and copolymer. SEM images revealed the composite morphology and uniform distribution of urea particle over the surface of the fertilizer and inside the fertilizer. Nitrogen release test revealed that this fertilizer perfectly follows the European standards, and also it helps to improve the sulfur oxidation, which in turn help the plant for their growth. It also prevents the economic losses and also prevents the environmental pollution.